we had a conversation about using analog readings on the 675, little 8-pin pick that we use for the automatic coach lighting and half of the PMPs. They were discussing how the analog system works on that chip, and it came up in the conversation that we were just pulling things like AD con equals 0 and AD res H equals such and such, and these random words out of the datasheet were appearing, and it was like we were speaking in Wizard. Why do these things just appear? So in order to explain that, I produced this little presentation, how to do hard JAL using microchips tools. I recommend that one to you. It's quite a popular one. And this, what I'm about to explain to you, is another version of that. I'm about to go through that with maybe some more interesting examples. I do recommend that though, because over and above what I'm about to say, it shows you how to install everything and why things fit together and how to make sure that things overlay each other and all that. Since then, I've also done a couple of others, one on serial monitors. I've got one in preparation on micro debugging. So there's quite a bit on there. The reasoning behind it goes like this. If we go back to a data sheet, here's the data sheet for the 675. Right, it's 2005 or something, and it's 132 pages, and of those 132 pages, about half of them are the interesting stuff, how to control the peripherals and how to make it work and all that groovy stuff. It has 2 banks of special function registers with 32 registers in total. This is knowable. You could learn that data sheet. It gets to the stage with that data sheet that you don't have to pick it up and look at it anymore because there's sufficiently little stuff in that. And if I compare that with a more modern data sheet, here's the 313323 data sheet, and there's 470 pages of it. And of those 470 pages, 420 pages are to do with the peripherals, because there's a shovel loads of peripherals there. And it's much, much more difficult to know these things, to learn these things, to understand these things. Again, there's 32 banks of special function registers. That's an 8-pin chip. And that 8-pin chip has 32 banks of registers, 512 special function registers. If you want to do something, you want to make a pulse width modulated output, then you have to set up the PWM, set up the pins, set up the timers, and that stuff's smeared all over these 512 registers, and it's complex. So to try and get past some of that complexity, Microchip brought out 2 systems. One of them, which we'll not be touching today, but I'm quite happy to talk about it some other time, it's called Harmony. And Harmony is for what I call big ticket items. Things like a USB bootloader or a CAN bus bootloader, a TCP/IP stack, that sort of big item. And what happens is they've written those pieces of software in a universal language whereby the same register is called the same thing irrespective of the chip. Let's say I write a CAN bus bootloader for one chip and I write it using Harmony, then I can pick it up and drop it on another chip and it'll mostly work. I might have to do a tiny bit of tweaking, but for the most part, I'm on the air. And MCC, the microchip code configurator, is the same sort of animal, but at a smaller scale. That's for the individual registers, the individual peripherals on the chip itself. And that's to make setting that stuff up much, much easier without the data sheet. This is good. The JAL group, the people that actually made and support JAL, responded to this in a couple of ways. The biggest of these is a thing called pick2JAL. Pick2JAL.py is a Python program that's in the JAL tools. As I say, if you refer to the hard JAL presentation, that will show you how to download the JAL tools. And what pick2JAL does is it takes any header file when when Microchip upgrade the MP Lab X, you get a whole new bunch of .h files, the header files for each of the chips, or the INC files, the INC files for the compiler. The Pick-to-JAL tool takes those INC files and converts them to JAL files, and it uses the same technique of converting the names in such a way that it's always the same. And so you get JAL libraries for each of the chips that are appropriate, and you don't have to write your own JAL for each chip as you go. So before we start talking about how to do this, there's a couple of things that I want to press upon people. First of all, if you're using JAL, you should keep it up to date. As I've explained earlier, if you go to the JAL lib page, it's a GitHub page. You can either do the GitHub clone trick, or you can download the zip, unzip it, and copy it right across the top of your JAL lib workplace. And that'll replace the compiler, or replace all the libraries, or replace everything with the newest version, and you'll be bang up to date. The other thing that's a possible thing is Visual Studio Code. Now, VS Code, the JAL editor, JAL Edit, that we're mostly using, was written by a guy called Sunish Isaac, and it was written by him in 2002, 2003, I think. He started on it, and he wrote it in Delphi, and he stopped writing it, he stopped upgrading it, he stopped supporting it in 2010, which is a decade ago. But it hasn't gone away. It's now available as a plugin to the Visual Studio Code system. Visual Studio Code is a coder's IDE. It's a light version of Visual Studio. You can get inputs there for JAL, obviously, for Arduinos, for Python, for C#, for C++, for whatever you fancy. You just pick the extensions you want and plug them in. I could do a whole one of these on Platform.io. Platform.io is a wonderful thing if you're programming microcontrollers, and I thoroughly recommend it as part of the Visual Studio. Now, why do I mention Visual Studio? It's got a couple of additions over and above JAL Edit. You've got a folding editor, so you can fold stuff up that you're not using. It's got improved highlighting of the syntax. It's got code completion, so you start typing a line and it fills it in for you, and all you have to do is tab through and change the bits that you need changing. The big one, though, is if you're using JAL Edit and you've got a big file, and if you're going to do what I'm about to explain to you, you will have big files. Then when you've got a big file and you've got two tabs open, if you go from one tab to the other, and one of those is a big file, then there's a context shift takes place, and JAL Edit is not quick at it, and it can take 5 or 10 seconds. And while it's doing that, you get nothing. There's no indication that JAL Edit is busy, and you think, I've hung up here, and you press a button or you stab something, and then JAL Edit completes, and it takes your other command, it does that, and it's very easy to get lost with JAL Edit when the files get big. There's no such problem with Visual Studio Code. And it's just the same, it's the same JAL compiler, so it's not as if it's any different. The other thing is there is no debugger in either JAL Edit or the Visual Studio version, but Sunish is still working on a debugger, and he's working for a debugger for the Visual Studio version. So it's worth having a wee think about, and I'll say no more than that. Now, to get down to how the hard JAL made easy thing works, there's 6 stages. The first one, and the simplest one, is can JAL use the chip that I'm on? I then start an empty project. I use MCC to set everything up. MCC will then generate all the code for me, except for my BSO code. BSO, Business Systems Options. It's if I'm making an EPOS system, an electronic point of sale system, then the EPOS stuff is the BSO, it's the business system. If I'm doing model railway code, then the BSO is model railway code. So the MCC will generate everything except the model railway part of it. I will then convert it from C to JAL almost automatically. And then I'll write my own model railway code or my own, whatever it is, code, which is usually only half a dozen or a dozen lines. First of all, we have to say that MCC doesn't support all the PIC chips. Because the PIC chips going back in history had different names for registers and stuff. Everything, the current Q series chips and the two versions before that, MCC will support, so there's no problem with that. If you go back to the old 675s or 877s or things like that, sometimes it was called Port A, sometimes it was called RA, sometimes it was called Tris A, sometimes it was called Trisp A, and all of the register names changed from datasheet to datasheet to datasheet. And so for that reason, Microchip has just cut all that stuff loose, no interested in it. Similarly, JAL no longer supports all the PIC chips because basically they haven't got around to doing it yet. It's a very small team and they're working hard, but they aren't keeping everything up to date. And there's some shortcomings in JAL Lib. I had a project to do for something recently for one of the members in WASAG here that involved doing a PWM, and he tried to use the PWM hardware library in JAL Lib, and it didn't work on a modern chip. Went in and looked at the PWM hardware library, and what the PWM library says, if you've got this register, do that. If you've got that register, do that. If you've got such and such a register, do that. Otherwise, finished. And it didn't even throw an error to say, I haven't loaded any PWM code. It was just written 10 years ago when there were only 2 or 3 chips with PWM and it could cover them all. But now everything's got umpteen different PWM techniques. And so that PWM hardware module just no longer works. So for that reason, you have to be careful with some of the JAL libs. Maybe talk about that at some other point as well. Now, my development environment, I use one of these things. Wonderful little toy. That's a 16F18855. £16. This is from Farnell, £16.20. I think I get given it at a meeting in a wee red box. It's a 28-pin modern chip, one generation ago. It's got 4 LEDs on it, it's got a little temperature sensor, it's got a single button, and it's got a pot. All the pins are scraped out to the 28-way jumpers, J7 and J8, on the outside edges of it. And it's also got this microbus or microbus interface. Now, the microbus interface is a SPI interface down one side and a I2C interface down the other side, and a couple of power supply pins and a couple of interrupts and resets and stuff, but basically it's just those 2 interfaces. The benefit of it is, though, that there are over 200 microbus peripherals about, and they cost from £2, £3, £4 up to, I was looking at one, it was an RF amplifier, a very, very complicated RF amplifier for microwaves. It was £40, but there's lots and lots of low-cost microbus peripherals, rotary encoders, MOSFET drivers, relays, switches, OLED displays, LCD displays, 7-segment leg displays, all the routine stuff that you want. You can get a microbus. So if I want to develop something for a PIC, 5 times out of 6, I'll pick this little board up, do the development work on it, because it's only that size. Goes in my top pocket. I can sit in front of the fire and do the development work in the laptop, and then go and start soldering when it comes to the final sort of stages of it. If you look 2/3 of the way down that board, there's a white line, and below that it says programmer. Now that's a 25Q50 chip that's down there, one of the more modern chips with USB on it. There's a USB micro connector on the bottom. If you plug that into a PC, your PC has a new drive, G drive or F drive or whatever. And it's only 128K, the F drive or G drive or whatever it was. But if you then take a file, something .hex, and drop it onto that H drive, then that file will be sucked in by that microchip below the line and will be programmed into the chip on top. No more PIC-Kit 4s or PIC-Kit 3s or ICD 4s or any of that stuff. This, all you need is the wee board and a micro lead. And it's very, very simple. What I'm about to explain to you about what I'm doing will take me half an hour to explain. It actually takes about 10 seconds to do. You can change something and press generate, press build, and as it builds, it copies it into the F drive or the H drive, and it puts it on the board, and the board starts. It's instant. You don't need to go through all that. You know, is my PIC-Kit 3 connected to it? Have I got a 100 ohm resistor in series? Any of that? None of that. You just, really instant, a really, really useful thing. However, I've also got its big brother. There's its big brother there, and that's the 18877. The 18855 and the 18877 are the same chip, all the same peripherals, except the 18877 has 40 pins, and it's available in PDIP, so you can get a meter or a scope probe onto it. And that's a simple wee prototyping board, simply to let me, again, do basic development stuff. You can see my 155 board to the bottom left of that picture, and the slightly bigger one with the 40 pin chip on it. So I'm going to do two examples. The first example I will walk through ponderously slowly. I mean, really, really, really slowly, right? The idea being that if you're watching, if you're sitting there with this, you'll be getting the presentation at the back end, so you can always go back. The second one, I will go a tad more briskly through because there's more detail in it. So I'll go a wee bit quicker through that. But please be aware that even the second one, I will be explaining it much more slowly than it takes to do it. You can do this in a few minutes. It really is quite simple and quite quick. So what I'm proposing to do is a microchip PIC, the 18855. I'm going to have a switch in the input, and I'm going to have a LED in the output. This, instead of using what is it, a 500 million transistor microchip, I could do it with one piece of wire, but I'm going to do it with a microchip anyway. So let's start with checking that JAL can use this chip. And all I do is I go to my JAL editor and I include the name of the chip, include 16F18855. And I press F10, the compile button, and it compiles. Down at the bottom, I got error 0, it compiled. If I had said it can't find 16F18855.jal, then that's the game stopped. That's the job over. Can't proceed any further. But because it did that, I know that I can carry on. Now, if I put my cursor in the middle of the name of the chip and right mouse, then down near the bottom, I can open the file at cursor. Just here, yeah. Control Enter, open file at cursor. And if I do that, I open the PIC to JAL file, 16F18855.jal. Now, I will, under no circumstances, ever change anything in that file. I'll only open it to read it. And the reason that I open it to read it is because it contains all the answers to every problem I'm going to have in the next half hour. The answer to it is in that file. The name of all the registers, the name of all the bits, the name of all the procedures, everything's in that file. I don't write to it, I don't change it, but I read it. I use that as my reference manual, if you like. So let's start an empty MP lab project. We've all done this, I suspect. We select the chip, we select the compiler, and away we go. Now, over to the left here, you will see that I have opened up the header files section, and I've opened up the source files section. There's nothing in either of them. A typical C project will have a file called the main.c. There isn't even one of them. This is raw, it's completely empty. And that's the position that I'm starting from, a completely empty project. What it does have is MCC installed. Now, as I said, the other presentation shows you how to install MCC. So what I'm going to do here is go to that little MCC shield and press it. And when I do, there's an explosion takes place. Look at the number of tabs that are on that screen and look at the number of tabs. Once I've told it to select MCC Classic, whoosh, there's suddenly a lot more tabs. Now I'm going to go back just a wee bit. Nowadays, you can get MCC Classic, which is what I'm using, which is on my machine. You can also get MPLab X to run on the web-based, whereby your project lives on a microchip server somewhere. And if you're going to use a version that includes the microchip servers, then you can use MCC Melody, whereby microchip keep everything up to date and all that good stuff. I don't. I just use MCC Classic and I upgrade it every 3 or 6 months or whatever. I'm not that much at the hairy edge, it has to be said. So I select MCC Classic and it opens like this. My little yellow thing is now down there. There are 2 tabs that are important. The notifications tab is the one that's currently selected. And what it does is it shows me anything that I should be thinking about, any information, any mistakes that I've made. If there's an error, it will appear there. If I've done something daft, if there's something that it thinks I need to know, it'll put a warning in there for me. And then there's the pin manager. Now the pin manager is this fella here with all the little padlocks. And that is where I select pins, output pins and input pins. Now, for this first experiment, it's just a switch to a LED. I'm not going to muck about with the clock. It automatically wakes up to the high frequency internal oscillator running at 4 megahertz, which is perfectly valid. A 4 megahertz internal oscillator will do fine for what I'm wanting. The watchdog timer switched off. Low voltage programming is enabled. You'll notice that because low voltage programming is enabled, that pin 1 in the chip up here, pin 1 is a different color. That says you can't put anything in pin 1. Now that's not because I'm going to use a reset. It's because I'm using low voltage programming, and the low voltage programming puts the VPP on pin 1 on the master clear input. So if I'm going to program with a PIC kit or a low voltage programmer, I need to have the M clear not in use. So I can't have that pin as an IO pin this time. So for that reason, if you look down here at the reset, bottom right, you can see that it's already locked. Pin 1's locked, it's been already in use, so I can't have it. Never mind, let's move on. I've now, if you look carefully at port A, I've selected port A pin 5, which is pin 7 of the chip. And I've clicked a wee padlock on it. So I want that to be an input. And in the line below, port A pin 2, I've clicked on that padlock. I want that to be an output. And if you look up at the chip map to the top right, you'll see that pin 4 and pin 7 have now got annotations on them to say those are in use as GPIOs. Right? That's all I want. One for my switch, one for my LED. So I can move on from that. And in order to move on from that, what I'm going to do is go up to the pin module and change the name. So the RA2, which is pin 4, I'm going to just type in there a new name. I'm going to call it LED because I'm wacky like that. And I'm going to call RA5 SW for switch because there's no holding me when I get started. And you'll notice that over on the chip that the name has changed. Pin 4's now got LED as its moniker, and pin 7 now has SW. Yep, and that's me done. The only time I have touched the keyboard so far in this exercise is to type LED in that little box and SW in that little box. But after I've done that, I'm now going to go and press the generate button. And at the generate button, MCC will make it so it will generate all the code to do what I've just asked it to do. And as I say, this is a really simple, a really trivial example, but it lets you see how it works. So having pressed the button, down here at the outputs, down there, over there, you see there's the output from MCC saying what it did. And over there in yellow, you can see all the files that it's generated. It's made MCC generated files directory in which it's put 3 header files, 3 H files, and 3 C files. And it's also made a main.c. So it has generated all these files for me. I don't know anything about, right? But because I've done this before, I do know what's in them, and I'm about to show you. In one of those files, one of those headers files, there's the code to set the tri-state for that lead. There's the code to set the latch for that lead. There's the code to set the port number for that lead. There's the code to change it to a weak pull-up, or open drain connecting, or make it analog, or set the lead high, or set the lead low, or toggle the lead, or get the value for the lead. Every possible thing you can do with a pin is there, right? And it's all written for me. And there's the same thing for the switch. Again, in those files already created. So I don't need to write anything. Now at this point, we could be doing this good stuff inside MP Lab, or we could do it inside JAL Edit. But in order to prove to you guys that I've got nothing up my sleeves, I'm going to do it in Notepad. So there's no seeing that there's anything clever going on. There's no software interacting with me or correcting anything or doing anything. It's all just done in Notepad. Main.c is the main part of the program. And if you open it up, it's 98% microchip sort of stuff. It's descriptions and licenses and EULAs and all that good stuff. And you can, if you notice, the /* to / is an extended comment in C. Most of those you can just cut away. You don't need them. And if you cut them all away, you get left with this. And anybody that's ever written any code for any microcontroller will recognize that. You've got a main, and the main's contents are initialize the system and then go around a little loop forever, and that's all about it. And there's also an include file, and that include file says include the stuff that MCC made. See it? I've just highlighted it in yellow. Now that include file in C, what happens? That means that at this point in the text file, you should jam in this other file. And if I jam that other file in there instead of that, I can delete that include line. So I could take that line and jam it in there, and I would no longer need that line. But if I look at that line, every header file in a C program has an associated D file. So there's mcc.h, and underneath it is mcc.c. Now, there's a declarator, I don't know how you say the word, for each of the functions that's in the C, but JAL doesn't use those. So those void system initialize void, that can go, don't need that, because I've actually got the definition downstairs of void system initialize void. So if I've got the code downstairs in the C file, I don't need that declarator. That's simply for the C compiler. But this won't be troubled by a C compiler, so I don't need it. And furthermore, If I then look at the includes that are included in MCC's include file, 4 of them that I've marked in red have got angle brackets round about the file name. See it, include xc.8. xc is the microchip C compiler. That'll not bother me. I'm going to compile this in JAL, so I don't need that. And standard in and standard out and standard bool and con.io, they're all to do with C. They're nothing to do with my system. The 2 that are in bunny rabbit ears that I've got quote marks round about them, those are local, those are in my directory, and those are the ones that I have to worry about. So let's have a look inside those, and those have got a lot of stuff in them, and each of them has got an associated C file. And again, all of these files are really quite small. They're half a dozen or a dozen lines. If once you've taken out, once you've scraped out all the comments that say this is a microchip licensed product, and if it goes wrong, it's your fault, not microchips and all that, happy bananas. But once you get rid of that, you get left with really quite small files. So having got what I've got, there's where they live. Main.c is in my main program, and there's a subdirectory called MCC generated files, and that's where all the header files live and all the config files live. So what I'm now going to do, well, that's a decision I've got to make. I could take all this code and put it into a great big JAL file and convert it. Take each line and convert it from C into JAL, and I'd be left with a great big JAL file that would compile. But we've already seen that JAL uses includes, so I can use includes in JAL. So I could equally well have lots of wee files that are all linked to each other. Each of those has got benefits and drawbacks. What I tend to do, and I've now done this many, many times, is I bring all the stuff into one great big file, I convert it, make it into JAL, and then I take the great big block of JAL and cut it and paste it into its own file called hardware.jal. And the hardware.jal contains all the garbage to do with the hardware, and I'm left with a little empty JAL file inside which I put my railway modelling type code. So that's what I'm going to do. And there's how I start. I've got the first line that I already put in. I've put my forever loop in to synthesize my main, and I've simply put some comments in for where I'm going to put the stuff from each of the header files and C files that I've generated automatically. So having done that, I simply copy and paste all that stuff in. As I say, I'm really explaining this really slowly because it's actually quite a quick process. And having copied it all in, I use search replace in JAL edit to convert it from C to JAL. First thing I do is comments. In C, a comment is // In JAL, it's --. So I can just tell it to search for all the // and replace them all with --. The next one is in C, we use #pragma_config, and we replace that in JAL with simply pragma target. So I can replace all of them boys as well. And in C, it tends to be on, whereas in JAL, it's enabled. Now, I've put a red flag on here. It's very tempting to simply say replace all. But if you replace all on the word on, then the word config will become enabled fig, because the on in the middle, it will get mangled. And on appears inside lots of words and lots of variable names. So you can't just use a bulk replace like that. You have to do it one at a time and go through them and say, yeah, replace you, replace you, replace you. Oh, no, you're precious. I don't want to touch you. So you have to do it a wee bit cautiously for that one. But similarly, off gets replaced with disabled. and so on. Eventually, it starts getting into this. Once I've done all the replacements, I now start using the compiler to do the work. I press the compile button and it gives me an error, unexpected token in line 6. And as usual with a compiler, when it gives you a problem in line n, you look at line n minus 1, and sure enough, on line 5, it's never heard of /define crystal frequency. That's okay. I know how to do that. I've done enough JAL to simply replace that. Now, what I do, it's my habit to, whatever I'm replacing, I simply put it in a comment before the replacement. That way, if I have to go back and revisit it, I can see what it was, just for security's sake. But you don't have to do that. You can delete it. So that's my first one. I've replaced that Pragma target clock. Next one, Pragma target fixed OSC disabled. Unknown target fixed OSC not defined. So at this point, I do the same trick as I mentioned before. I put my cursor into the name of the chip. I right mouse it. I open the file, and inside the reference file, I look for whatever it is I'm stuck on. As I say, fixed OSC, all the answers are in that file. They have to be, because they were put there by the JAL program that was put there by the microchip program. So if it's not there, microchip didn't do it. And digging through it, I find there's one reference to fixed OSC here, but it says that this is to do with the fuse definitions, and it's actually, from reading it, what that part of the code is trying to do is it wants the external oscillator to be off. Well, external oscillator off, I can see how to do that from here. This is JAL. So in JAL, all I need to do is say Pragma os off. So that's what I do. Pragma target oscillator off, and I'm done. I press the compile button again, and it goes down half a dozen lines, and there's something here called MCLRE that it doesn't understand. MCLRE enabled doesn't make sense. So I go over to the other side. This is why I was saying that these big files in JAL edit, sometimes the flicking back and forth can take time, so you've got to be careful. I go over to the JAL file and I search for MCLRE, and I find it's actually now called MCLR, is either external or internal. And now that I've found that MCLR is either external or internal, I'll go back in and fix it. MCLR external. And now it's went down another couple of lines and it's found something called the boron that's to be enabled. And it's probably brownout instead of boron these days. Remember I showed you all the stuff that you can do with lead? This is me now going through that and converting lead tris A underline tris A2. The lead latch is lat A underline lat A2, and so on. And those little set the lead high, there's the code in C, and underneath it I've made a tiny wee procedure in JAL to set the lead high. One line, latch A2 becomes equal to 1. That's enough to set that lead high. And it's just a conversion of that one line of C to one line of JAL. And you can do that for all of these little procedures. Now, there's dozens and dozens of these wee procedures, and I'm not using most of them. I'm only going to use read the switch and write to the lead. That's all there is. But they're all there. Now you can convert them or you can delete them. I tend to convert them because one, it means I've got the code on my machine in case I ever need it for anything else. And two, I may not be certain that some of Microchip's code isn't going to use some of this code. So Microchip, one of its other functions may decide to set a latch or check something or do something. So I don't want to break Microchip's code by deleting microchips code. So for that reason, I tend to hold on to it. It's not a major issue to simply convert it. It's good practice if you're writing a lot of JAL anyway. It just keeps you sharp. The way that things are defined, if I define things in C, it doesn't matter which order. That's why C has got those declarators that I mentioned earlier in the header file, where it tells you what functions you've got. JAL doesn't have those. So for that reason, in JAL, you can only call something once you've declared it, once you've actually made it happen. So if my JAL compiler came down through here and it found system initialize, and the first line of system initialize is PMD initialize, but if it's never heard of PMD initialize, at that point it says, I've never heard of that. So what I've got to do is convert PMD initialize, pin manager initialize, and oscillator initialize. Those have to be converted and then put above system initialize in the firing order. I simply have to make sure that they are above where they are called in the JAL program, because JAL works like that. In JAL, you can only use something once you've declared it. I'm sure that everybody here's well au fait with that. So you have to remember it though when you're doing this. There you are. So by putting the PMD initialize and all that good stuff above system initialize, it successfully compiles. 41,000 tokens. 365,000 characters, 7,000 lines, a lot of stuff to synthesize a wire, but never mind. It takes 65 bytes of code, so it's not that big either. I now cut all of that demo code and paste it into hardware.jal. Bump, and it's away. And now I include hardware.jal at the top of my program, and I put the code to do whatever I want to do in here. This is the model railway code, if you like. Now, this is very, very simple. As you can see, I've declared a bit to be a yes or no, and I go around my forever loop, getting the value from the switch, which happens to be line 160 in hardware.jal. If the switch is 1, then I set the lead high, and if the switch is low, then I set the lead low. And the set high, set low, get value, they all came from the conversion that I just did inside hardware.jal. And at that point, it works. Now, at this point, I had a video to show you. The finger of God comes in from the left-hand side, presses the blue button and turns the light off and goes away again. But if I include that, the download for this presentation goes from 45 megabits up to about half a gigabyte. So I didn't include the videos. I've simply left a picture of them. But trust me, they work. So I'm now going to move on to this second example, which is a wee bit more beefy, a wee bit more interesting. And I'm not going to go through it step by step like that. I will sort of breeze through, but hopefully you'll see something that's a wee bit more interesting. Right, not everybody has used a remote control servo, so just for those that haven't, I'm going to remind you that what I need is a repeating pulse that repeats every 20 milliseconds, and that pulse has to be between 1 and 2 milliseconds. So I'm going to do that, and how I'm going to do it is this. I'm going to make a pulse using a timer that repeats every 20 milliseconds. What the size and shape of the pulse is, don't care. Not giving a toot. As long as it repeats every 20 milliseconds, that's all I want. From it, I'm going to use it to trigger 2 other pulses on 2 other timers. The first pulse, which I'm calling X, will be 2 milliseconds long, and it'll be fixed at 2 milliseconds. The third pulse, which I'm calling Y, will be somewhere between 0 and 1 millisecond, and it'll be triggered at the same time by this 20 millisecond pulse. If I then take not X and Y, or if I take it when X is low and Y is high, then I get a pulse that is between 1 and 2 milliseconds and repeats every 20 milliseconds, which is exactly what I want. And I'm going to use 3 timers and a little bit of logic to do that, and no code. So how are we going to do this? First of all, the circuit. I'm going to take an input from an analog to digital converter. Little blue pot on my board. I'm going to use that to the pick. The pick is going to autonomously make that servo track the knob on the potentiometer. Let's start another project. I'll call it auto servo. This time, if I go over to the left-hand side, I see a list of all the resources that are available for my chip. Right, I kind of pulled that down the last time to see the project files, but this time I'm going into it. I'm going to start and use some of these. Before I do, I'm going to play with the system tab. I'm going to use the high frequency internal oscillator. I'm going to set it to 8 megahertz, and I'm going to set that to divide by 4. 2 reasons for that. First of all, just to show you boys that I'm not feared to changing the system tab and mucking about with the oscillators. And secondly, because I found that if I used the 4 megahertz oscillator, that my delays weren't always crisp. Instead of 2 milliseconds, I'd get 2.004 milliseconds, or instead of 20 milliseconds, I'd get 19.996 milliseconds. Whereas if I use this system, I get it crisp. And because this thing is so easy to use, it was a case of try that, nope, go round, try that, nope, go round, try that, nope. And within 3 or 4 tries, I'd worked out that I could get much better results with this high frequency internal oscillator at 8 megahertz divided by 4. So there we go. Before I touch any of the resources over to the left, I pick the high frequency oscillator, I select 8 megahertz, and I divide by 4. As ever, I'm keeping my eye on the notifications tab at the bottom. Next, analog to digital converter. So I'm going to pick an analog to digital converter. I'm going to make it run continuously. I'm going to make ADC run, and as soon as you've got a result, start the ADC again. And however long it takes later, it'll replace that value and start the ADC again. Just free running ADC, no starting it and stopping it and demanding it and any of that stuff. I want the results to be left aligned so that I get a value between 0 and 255. And I want to take the value from my little blue pot, which happens to be pin RA4 on my board. So here we go. Pick an ADC, click on plus, left align, enable continuous operation, and then I go down to the pin manager. Because I've added an ADC to my setup, when I go to the pin manager, the ADC pins are there. And so I can now tell it, where's my AN input? Well, my AN input is going to be port A4, RA4, because that's where the pot is on this board. It's soldered to pin RA4. Right, that's good. So now I got up to the pin module. Remember, I changed the name of the thing to LED and to switch. Well, I'm changing that to pot because I'm still as wacky in my old age as I was this morning. So here we go. Pot is what it's called. Right, that's it. That's the analog to digital converting done. I'm now going to add a timer, timer 2, which is going to be a 20 millisecond main pulse. Again, I've discovered that the clock source is going to be the low frequency internal oscillator, preset to 1 to 4, and that will bring 20 milliseconds into range. I'll explain that now. Over here, over to the left, I picked timer 2. When I select it, I get a timer 2 tab. I've selected my low frequency internal oscillator, 1 to 4 for the pre-scaler, and in that box at the bottom there, that one over there, I put 20 milliseconds. And when I put 20 milliseconds, it gives me the actual period that it's going to calculate. If I change the pre-scaler, then the timer period limits change, and I have to pick the value in between. And I found that with a 1 to 4 pre-scaler, when I asked it for 20 milliseconds, it gave me exactly 20 milliseconds. So that's it. That's all I need. That's working. The panel at the bottom hasn't given me any warnings, hasn't started telling me that I'm doing anything wrong, so I can push on. Timer 4 is going to be my 2 millisecond pulse. I'm going to use the fixed oscillator divided by 4. I've discovered by playing with it that if I set it to 1 to 8, I'll get my 2 milliseconds will be in the range. And once 2 milliseconds is in the range, I'm done. And I'll then set it to 2 milliseconds. Now here's a wee warning. Timer 4 has to be triggered by timer 2. So it has to be a monostable timer, and it has to be controlled by timer 2. So let's do that. First of all, set the fixed oscillator, set the pre-scaler, put the 2 milliseconds in there. 2 milliseconds is between 16 microseconds and 4 milliseconds, right in the middle. And it calculates an actual period of 2 milliseconds, which is exactly what I want. And now I've got to do right now it's a rollover. See at the top there, it's going to just roll over and roll over and roll over. Don't want that. I want it to be a monostable. And when I tell it it's going to be a monostable, it says, and how are you going to reset your monostable, sir? So I tell it I'm going to reset it by timer 2. And at this point, the notifications panel at the bottom has started kicking in. It says, check, you're using timer 4 off of timer 2. You better have set up timer 2. Now I've set up timer 2, so I don't care. I'm okay. I'm cool with that. But it's just warning me that if I'm going to use timer 4 triggered from timer 2, then I better make sure I've got a timer 2 that makes sense. So on. Timer 6 is going to be monostable again. It's going to be triggered by timer 2, just the same as its neighbour. It's going to have the same source, slightly different pre-scaler, because I want this to be 0 to 1 millisecond, and this is the one that I vary by jamming numbers into. And if I jam the numbers in, I want 0 to 255 to correspond to 0 to 1 millisecond. I want to use all of the 256 options there. So for that reason, I want the 1 millisecond to be right at the top of the range. So I have to play about with this a little bit. Set it to monostable, set it to timer 2 post-scaled, f-osc divided by 4. Again, the pre-scaler at 1.1 to 2. The previous one was 1 to 4, and that gave me between 8 and 16 microseconds and 4 milliseconds. If I set it to 1 to 2, I can make it 1 millisecond, but it's 1 millisecond out of 1.024 milliseconds. So that means that if I jam a number in there between 0 and 255, I'll get a timer that goes between 0 and 1 millisecond, which is exactly what I want. Meanwhile, the notification thing is going crazy. Now you've got another timer. Timer 6 is running off timer 2. You've got to make sure you've got timer 2 configured. I have. I'm cool with it. I'm moving on. Now, remember this bit when I said I'm going to use not X and Y logically. In order to do that, I'm going to use a peripheral on the side of the chip that's called a CLC, a configurable logic cell. I'm going to use it in AND OR mode. Now, if you've not come across CLCs, and this might be a new one, they're like a little lump of digital logic that you can configure to be any type of logic you want or within reason. The CLC on the PIC chip has got 8 modes. Let me show you. It can be a D-type flip-flop, it can be a transparent latch, it can be a D-type flip-flop with just a reset, it can be a D-type flip-flop with a set reset, it can be a 4-input AND gate, it can be an AND OR chain, which is what I'm about to use, that one at the top left. It can be a JK, an XOR, or an SR latch. If you've ever used programmable logic devices, either CPLDs or FPGAs, you'll recognise that what we're actually dealing with here is a thing called a macro cell. And basically there are some wee macro cells built into this PIC. So my CLC is going to be in AND OR mode. One input is going to be timer 4 inverted. Remember I said not timer 4. And the other one's going to be timer 6, not inverted. And then the output of that is what drives my servo. So that goes to a pin in the side of the chip. I go over here and I select a CLC and I drop it onto the image. And I'm going to zoom right in close. And I simply pull down there to select timer 4 for my input. And I click that little circle there. If you click these X's, it goes through 3 modes. It's either connected straight. Look at the timer 6 one, it goes straight into the gate number 2. Or it goes in inverted. If you look at gate number 1, my input there goes in inverted. Or if you click it again, it turns an X, in which case it's not connected. So at this point, I've got not timer 4 going in through gate 1 over to the AND, which is just at my head here. And I've got timer 6 going straight through, straight to the AND, in through my ear. So that AND gate is going to be not timer 4 and timer 6, which is what I reckon the logic was for what I was wanting to do. And I need to select a pin. Port C7 is the pin nearest the edge of my wee board, so I'll use that for my servo. And I'm done. Again, I haven't done any. I've been pick that, pick that, pick that, pick that, pick that, pick that. It's taken me 20 minutes, half an hour to explain it. It took me 3 minutes to do it. It's not difficult. So I generate it and I build it. I get all the usual stuff. If you look over to the left here, MCC has generated a bunch of files for me this time. So it's going to take a bit longer to wade through them doing the conversion, but that's all right. If you look down at the bottom left, I have used 185 bytes of my 8K. So I've used practically nothing on this. And I don't have any program yet. Now, because I'm doing this, I've got this much work done. I'm going to make sure that it works before I convert it to JAL, because it's a simple wee thing. So it doesn't take much to convert it to JAL. I get the code to start the converter running. I change the channel from being whatever it is to pot, and I find the code to jam numbers into timer 6, and that's all I need. So I've written a C application, initialize the system, start the A to D converter, and then forever set the 8-bit period to whatever the ADC is. So I take the value from the ADC and I jam it in the 8-bit timer, and that's it. I check it and it works, and away we go. So I now copy all the cruft as I did before to JAL edit, and I translate it exactly as I did before using the same techniques, the conversion and then the replacement, and then using the compiler to find the bugs. The one thing that's different is the more complicated bits of C will use a thing called a structure in C called an enum. An enum is like if I declare something called a colour, and colour can be red, green, blue or brown, then red's got a value of 1 and brown's got a value of 2 and blue's got a value of 3 and so on. And basically that just converts into a series of constants in JAL. So if you ever come across an enum like that, all you need to do is convert it to half a dozen constants and it'll work just fine for you. And here we are. I've done all that now in JAL. I've converted it all, and I've now converted it all to hardware for AS. And there it is running. Setup, system initialize, ADCC, start the converter, that runs the ADC. And then my forever loop is get the pot value and set the servo to the pot value. At no point do I go and set the pin high. At no point do I worry about the timer. At no point do I set the servo pin low. At no point do I have to worry about 20 millisecond time. All that stuff is being done autonomously by the peripherals on their own, speaking to themselves. I simply say, there's the value I want. Right, and that's it. That's the code, and that runs beautifully. Again, another little video. If you want the videos, I'll put them up, but there's not an awful lot to see. That good looking fella twiddles his wee blue pot and that wee servo horn goes round about, and it works absolutely perfectly. Now, just before I finish, some further thoughts. The code that I've written is much, much smaller than if I'd done it with an Arduino or with a smaller PIC. There's the Arduino. I wrote it in Arduino. This used to be one of the standard, you know, the examples in Arduino under file sketch example. It's not there anymore. However, it's not hard to write. It takes 7% of the Atmega 328 to put a simple servo like this in. And it uses your only timer. And it's blocking. While it's doing the servo, it can't be doing anything else. So you have to either write interrupt handlers to control the lines going up and down and all that happy stuff, which I haven't done here, or you have to find some way of making your code work in between the servo. So it's much more complicated in the Arduino. Similarly, there it is for the 12F675. It takes 112 of the 1023 bytes of the 675 to do it. And again, it's blocking. It will not, you can't use the chip while it's using the servo. You have to find a way of making them get on each other, and that's non-trivial. So, could I expand this? I can expand it up to 4 channels without having to think about it. I could put in frog relays, I could put in, let me just have a look at this. There's the circuit that we're currently using. Timer 2 is the 20 millisecond timer, and it triggers timer 4 and timer 6. And timer 4 and timer 6 go to the logic cell, and that goes to the servo. The 20 millisecond timer would be the same 20 millisecond timer for every servo I use. I don't need a separate 20 millisecond timer every time. And the 2 millisecond timer would be the same for every servo I want to use. So by that logic, I could simply use the other 3 timers that I've got spare, and I've got another 3 CLCs, and I can simply drive 4 servos off this chip and still have timer 0 available. JAL uses timer 0. So I haven't interrupted timer 0. Timer 0 is still there for my main JAL code for writing whatever it is I want to do. Flashing LEDs or operating signals or whatever I want to do. Timer 0 is still there for me. But I've used the other 6 timers to keep the 4 servos operating automatically, so I don't have to think about the 4 servos. If I wanted to put frog switching relays in there, easy. 8 analog inputs, yep, I've got 24 analog inputs on that chip. I could put 4 digital ins to trigger it. The 8 analog inputs would give me a head and branch for each of my 4 servos. So I could set it up as an 8 pot servo 4, if you see what I mean. Right, and so far I haven't really done anything. I could trigger it from digital inputs. I could trigger it from RS232 or I2C or CAN bus, LIN bus, everything in that list except for DCC, LCC. The rest of them, I can include those triggers by dragging and dropping inside MPLAB. I don't have to write the code for that. DCC, I've got a library for. LCC, I've got a library for. The rest are drag and drop. I've got 25 pins on the 28 pin chip to play with. I've got 36 pins on the big chip to play with. So there's lots and lots of scope there. Now, the various URLs that I've mentioned are on the screen now. You'll be able to see those. You can copy and paste those if you want to look at the WASAG site or our videos. The usual stuff for getting MPLabX plus the data sheets. And that little dev board, I've put up Farnell's link for that. You should have probably already know where to get JAL edit and where to get JAL lib. So at that point, I'll list the software that I'm used, the versions, in case you want to try and step through this on your own. Because I'm finished. Any questions from anyone?